A YouTube channel, right? One strike towards a YouTube channel for showing kids getting hurt on merry-go-rounds. So you get that's how you get a strike, and then if you get a couple strikes, then you're out for a while, and then if you do another one, then you're out for further fight. Anyways, it's a fascinating channel, right? If you're looking for something to do, you can go look at that anyway. All right. So what we were talking about is how things go into orbit, right? To me, this is really cool, right? Because this is within, just a couple of days worth of lectures, we get to a point where we get what's happening here, right? There isn't much happening, right? You got something that's traveling around, and then we drew our little free body diagram right here, right? Drew that little free body diagram, and there's only one force acting on it, right? The force from gravity. And we have our coordinate system, ER and E theta. Right? That's it, right? That's all that's happening on this system right here, okay? And so we went over here and we drew our little free body we drew our equations of motion, right? We have just negative Fg is equal to mass times acceleration, right? That's how it works. It's equal mass times acceleration. If this thing is not falling back towards Earth, if it was falling back towards Earth, right? If it was falling back there, we would have an R double dot, right? We would have something there, but it's not falling back to Earth, so there is no R double dot. And so all you're left with is this R omega squared term. And if we put that in terms of velocities, we get this, right? The force due to gravity is equal to mass of the satellite times v squared over r. So we can figure out what that velocity needs to be to hold it at that orbit, right? Again, if it wasn't being held at that orbit, it would be accelerating back down to Earth, and you'd pick up an r double dot, but we don't have one. It's going to be in a stable orbit. So we can determine the velocity required for it to stay in orbit. Okay, so that it doesn't fall back down to Earth, right? If we substitute in what gravity is, we can't just say gravity is 9.81 meters per second squared, because now we're dealing with things getting far away from Earth, right? And in that situation, we have to use Newton's gravitational equation right here, which is G is a constant, right? Mass of the Earth. We know mass of the Earth. Mass of the satellite actually cancels out. I know the radius of the Earth. I know the height above the surface. And this velocity you're going to have is going to be dependent upon the height, right? And it should be dependent upon the height, right? The closer I am, back to this analogy, the closer I am to the surface of this Earth, I better be going faster, right? Because I got to be whipping out fast enough so that it makes it around that corner before it hits the ground. But if I go further away from Earth, I don't have to travel as fast, right? Because the Earth is way far away, and the Earth is curving underneath me faster than I'm going around there. So there's a lot going on. Just with that right there, right? We just took that, we substituted it in our knowns. We came up with an equation for the velocity as a function of height. We substituted in what gm Earth is, right? Those are actually two different constants. There's G, the gravitational constant, and then the mass of the Earth. But right, we substitute that value in, and we can solve for the velocity. And so if we look at the International Space Station, we know the height of it is 340 kilometers above the surface. We substitute that in, and we get the velocity of the International Space Station is 7.7 kilometers per second. In things that we know how to interpret is 70,224 miles per hour, right? So that sucker's booking, right? So when you see a satellite being launched into space, right? You see, obviously it comes up, you got to get the elevation, but once you get to that elevation, then it's got to get to 17,224 miles per hour in order for it to stay in orbit. If it doesn't get going that fast, it's going to fall, okay? I think, isn't that kind of cool? And then, so if you look it up on the internet, guess what the internet says that's going? About 17,000 miles per hour, right? Which is, to me, that's cool, right? Like just these little calcs, one page of calcs, we could determine that. I don't know. You guys seem less impressed than this. I think this is impressive. That just like that, we can calculate that, and that is really what it is. There's nothing really else acting up there. I mean, yeah, there's some. I believe I'm not that kind of engineer, but I think there is some resistance up out of the atmosphere. There's like little things hitting it. Anybody know little protons or something? Well, I can tell you whatever you want. You don't know either. So there's protons, there's loose stuff. There is stuff there that is causing a little bit of drag. So every once in a while, the satellite does have to adjust its velocity. It does have to put a little energy into the system to get going. But once it's up there, and then when you see on the movies and stuff, it goes from like, they go from being like, being pushed against the back of their seat when they're flying up, and then it just goes boom, cuts. That's what it is. Because as soon as they get up to 17,224, they cut off those thrusters, and then boom, all forces are gone. Right? Gravity's there, and they're constantly falling. What's kind of interesting to think about is like they're constant. That's why they're weightless. Is they're constantly falling towards Earth at all times. It's just always falling towards Earth, but their velocity this direction is fast enough that it doesn't actually ever hit Earth. And so then it goes from however many G's of force they feel to get up to 17,224 to nothing. And then it's just like weightless, and then you're falling. I don't know, it's pretty cool. Okay, so that is for the International Space Station, right? So this is the other thing. I'm going to teach you something else that I didn't know this until I started teaching this class. Was right? You got back in the day, there's things called satellite dishes. I don't know if that's a thing anymore. Is that a thing? Your parents have like DirecTV or something like that back in the day, right? Or in my day, they weren't little guys. They were big ones, right? And if you had literally kids in the neighborhood, their parents had these big, massive satellites, satellite dishes in their yards. You just walk over and there's a big old dish, a huge one, right? And I never understood what was happening. Like I say, I know how a satellite works, right? It's right whipping around the Earth. And then these guys, you go, you set up your satellite dish and you point it in one direction, right? You don't ever change that direction. You just point it that way, and then it's talking to something. I was like, I don't know what the fuck it's talking to, but it's talking to something. What it's talking to is a satellite, right? And that satellite is fixed in space. You're like, how the fuck is that happening? Isn't that kind of interesting thing? Well, how is it? If it's got to be going, right? It's got to be traveling that way because it's going to fall down to Earth. But how can you get a satellite that's fixed in space? And that's and what that's called is something being in geosynchronous orbit. And so what happens is they put it really far away, right? So that when it's traveling around like this, it's the same speed that the Earth is traveling around. So that when you're out there, you're looking, and there is a satellite there, but it's tracking with you. It's moving at the same speed that the Earth is moving. So it's talking to a satellite. So you can calculate how far away that satellite has to be in order for it to be in geosynchronous orbit. Pretty easy with what we just derived. Let me do that just really quick. It's actually a pretty easy calculation. Right? So what you do is you think about, what you want to be equal. What's really interesting is I just did this calculation on my own one day. I was just like, I think that this would work. And then I calculated, this is a true story, and I calculated it, and I was like, oh, and I calculated the height. And then I went to the internet afterwards, and I found out that is the height that geosynchronous orbits are at. I was very proud of myself that day, right? Because I'm a structural engineer. So like this, you may be like, oh, my physics teacher taught me this years ago. I didn't know it, right? So if you take the velocity, right, the velocity of your satellite, and you multiply it by 1 day, right? Because that would tell me the circumference that satellite would travel, right? If I have the velocity of that satellite, which is distance per time, right? And I multiply it by 1 day, because that's 1 day, that's one revolution of the Earth. If you believe in this stuff, the Earth turns around once per day, right? And so it just makes it once per day. So you have velocity times once per day. That would tell me the total circumference that this thing would travel, right? That's the distance that the satellite would travel, right? And then I'd set that equal to 2 pi times our Earth plus the height of the satellite, right? Because those should be the same, right? 2 pi, right? This is the circumference of a circle, right? The circumference is 2 pi times the radius. Well, in this situation, the radius would be the radius of the Earth, right? Because all these things are based off the center of the Earth. So you have the center of the Earth, and then you go out a distance h from that, right? And so that's my circle. 2 pi times the radius is equal to the velocity times 1 day, right? And there's a little bit going on in terms of like units, obviously, right? Velocity, the equation that we have up above is in kilometers per second, and then my day, so I gotta get my day into seconds. But if I do that, if you just carry this thing out and do your do your conversion for how many seconds are in a day, right? And then solve for h, right? And we solve for h. Right? Yeah, convert to seconds. I'm not going to do that, but right, convert to seconds. And then what you get is h is equal to 35,861 kilometers. And those of us Americans would call that 22,284 miles. Okay? So something that's that far away is what we call geosynchronous orbit. Yes?
So where are you getting your velocity from?
Oh, yep.
Wouldn't it be omega?
Yeah, it's this. Yeah, it's that equation that we derive for the velocity. Yeah, actually, I should have pointed that out. Right, so you put that down there, and then so there's h in that, and then there's h on the right-hand side, and calculator, and then I'll pop this. So there's 35,861 kilometers, or 22,284 miles away. So, right, International Space Station, 340 kilometers above the Earth's surface. Things in geosynchronous orbit, 22,284 miles away from us, right? So these things are way out there, right? So that when you're, I don't know, sometimes I think your direct TV cuts out sometimes with the bad weather and stuff like that. It's talking to a satellite that's 22,000 miles away. Like, give it a break, right? Like literally. And then like when you're out there trying to set it and trying to, because you have to go out and you have to set it up and try to point at the thing. It's got to get right at it. Well, my God, it's 22,000 miles away, right? Of course it's going to be difficult to set up that thing up, right? To show you like a scale, that's what this is the next graphic here. I don't know if I included this in your notes or not. Is this in your notes? It's blurry, you can't read it. But these are, right, just to kind of show you the different orbits. I think I have a high definition one that I can share with you guys, right? But there's, the surface of the Earth, and then there's the self-propelled jet aircraft is way down here. Sputnik was right here. Right? International Space Station is right here. Okay, so that's where the international. So then you get from this perspective, when you actually see the curvature of the Earth, you understand why this thing has to be going 17,226 miles per hour, right? You absolutely get it. It's got to be booking. I mean, it's really close to that picture that I drew of the guy throwing the ball, right? It has to be booking in order for it to make it around the Earth like that. I thought that was pretty cool. Okay, and then you can kind of see some of these other things where Hubble Space Telescope looks like it's 505 kilometers above the Earth's surface, right? And so these are called near-Earth orbits, right? Because they're right next to the Earth, right? And they're whipping around like that. Can you imagine, like back in the day, like with like Sputnik, and then like the dogs are like, I think this will work, right? And they sent a dog up. I think this will work. Let's just get a big rocket, right? And let's launch that shit up in the air, and then let's get it going. And I bet you, if we get it going fast enough that way, it'll clear the Earth and actually make it around. They did this at one point, right? They did this in the 60s. Is that when this went down? Right? It's like, holy shit, right? You know what's really fucking amazing? Is we made it to the moon once, right? Like, allegedly, right? Right? I mean, literally in the 60s. If you ever ridden in a car from the 60s, right? It is terrifying. It is absolutely, the steering wheels, like they got a bunch of play in it. There's no power steering. It's like, we went to the moon with that technology, right? That was the level of technology. We're like, let's fucking do it. Let's go, right? We haven't been back since. Nobody's been back since, right? It was 1969 the first time that we landed, right? God, we haven't been back yet. What the fuck, right? Like, my God, right? Look at all our technology right now. Like, let's nut up and go, right? Let's do it, right? I mean, Neil Armstrong just went, man. Allegedly he did it. To me, that is phenomenal, right? Ride in a car from the 60s sometime and then go, oh my God, right? Guess what they had for calculators back in the day? They didn't have shit, man. They didn't have nothing, right? That TI-89 would have been phenomenal back then, right? The kind of tools we have now, damn right we should be up there again, right? There's a lot of arguments. Well, maybe we don't need to do it because it doesn't help. Yeah, damn right it helps, right? Like, think all the good. We're pushing the limits of humanity. Let's go. Let's go to Mars. I mean, I don't want to go. It's terrifying. But it's you young kids. You go out there, okay? All right. So that's near Earth orbit, right? And we come out and just to show you perspective, right? So this is. So your GPS, like you're on your phone, which is, again, technology that we have now that you didn't have then. You have GPS on your phone that's talking to satellites all the time. Your GPS on your phone or GPS, devices and stuff like that, they're talking to satellites, right? They're talking to 3 or 4 at a time, right? And that's how they are able to tell where you're at. So they're talking to a couple of, I think you need 4, you need 3 to tell position, you need 4 to tell elevation as well. But anyways, it's talking, doing it, triangulating, it's doing all the geometry and stuff like that. It's working around. Those satellites that you're talking at are coming around the Earth twice a day. So they're out here. That's what these guys are. These are your navigation satellites. So they're whipping around the Earth twice per day. So they're circling twice. As opposed to being in geosynchronous orbit, they are going around a couple times. And there's a bunch of them, and they're circling around different parts of the Earth. Okay, so that's that one. And then this out here, this is where our geosynchronous orbits are at. Right, so they're way out there. Right, and again, what's happening for this kind of perspective, you kind of see it like the Earth is going to start rotating like this. And then that thing is just travels with it like that. Its orbit is just lines up perfect as the Earth rotates around, right? That's kind of cool. I thought that was cool to learn about, right? And so then when you point your satellite, that's what it's talking to. Yeah.
So you keep saying that when you're closer to Earth, you go faster, but wouldn't it be the opposite?
No.
No? Because the equation...
It's on the bottom. The height's on the bottom. Right? It's gonna be whipping, right? And it just from this perspective, right? It's gonna be whipping, because otherwise it's gonna hit the ground. But you go far away, then it doesn't have to hit the ground. Because the height's on the bottom, right? It's inversely proportional to the velocity equation is inversely proportional to the height. Right? So as the height gets bigger, the velocity goes down. Right here on the bottom. But I get it. Yeah, I mean it is confusing, right? And so then that thing's whipping around like that. I thought that's kind of cool. So then you can also, I thought this is me last night, me and ChatGPT having a conversation around 6 last night. I was like, you know what? Like, I go, I bet you somewhere in our history we use this to determine something. So I originally thought, well, maybe they use this height to determine the distance to the sun. Right? Like why not? We can figure out the distance to the sun. But then immediately I was just like, wait a minute. In order to determine the distance to the sun, we would have to know the mass of the sun. Right? You need to know the mass of the sun. We don't know the mass of the sun. Right? So this is literally what they did. Look, me and Chad were talking last night, and it was what they first did is they determined how far away the sun was. Right? And how they were able to do that was with, I have no idea. Okay, so it involved Venus. Venus went in front of the sun, and then they were able to make some calcs off of it, like from the sun. And then later on in a different part of the world, it went in front of the sun, and at the same time, and then another part of the world, it went in front of the sun at a different time. And then they were able to tell, based off triangles, I'm guessing, that the sun is 93 million miles away. Right? Somehow they did that. So Chad tried to explain it to me, but I was too dumb. And then, so we figured that out. So then we got that. So then if we knew that, right? If I know, and so that's what they did. And so they actually used this to determine the mass of the sun. So what they did is they came slightly different. We'll talk about that in a second. So G, the gravitational constant. Let me look at that thing. Meters cubed, kilograms per to -1 seconds squared. Anyways, G is a known number. Mass of the sun we're after. I don't know the radius of the sun, but I do know that it's really small compared to the distance to the sun from us, right? I mean, the radius of the sun is really small. So that's small. Let's just neglect that. I know that the Earth goes around the sun once every year. I know the time it takes to do an orbit, which is 1 year, and in seconds, that's 557,600 seconds, right? And then again, I just do 2 pi. That's plus the radius of the sun plus the height. But again, radius of the sun is really small. That's that. And then if you calculate it out and you solve for mass of the sun, That's what you get for the mass of the sun. 1.985 times 10 to the 30th kilograms. Okay? And then guess what the mass of the sun is? It's about that, right? Guess how they determined it? Like this. Isn't that kind of cool? Like this was back in the day. These guys with no calculators and we're just like some ideas, and they were like, oh, I bet you we could calculate this stuff. And then they were probably, right, like, didn't Galileo get like locked up and stuff? I think he did, right? Because he came, what's that?
Setting fire or something?
He's just setting fire or something. He got something, right? Because he came out and said, oh, hey, the earth rotates around the sun. And they're like, what? You blasphemy. You're dead, right? We're gonna burn you, right? I mean, and I think he escaped a lot of it, but there were a lot of people that did happen. And my God, despite all that, they were able to come up with this. The one difference between that, they use something slightly different. They use Kepler's law for this stuff. And what it is are we really traveling in a circle? We're not. It's kind of like an elliptical orbit that we're in. And so, and same thing with a lot of the planets are in kind of elliptical orbits around the sun. And all of this assumes a circular orbit. And so, but you get pretty damn close. Anybody else you think this is cool? I think this is cool. I'm like a kid working this out. Let me just show you too. You should use ChatGPT when you can, right? Right. This is my conversation with it last night, right? How fast is the ISS traveling? Yeah, and it's like 17,500 miles per hour. It's like, no, come on. Can you sharpen your pencil and come up with a better answer than that? And then it did, 17,138, right? And so that just shows you, we came up with 17,222, right? Was what we came out with, right? What is the height of the satellites in geosynchronous orbit, right? 22,284 miles, right? I mean, that's really close to what we just calculated. What is G mass of the sun, right? And then this is me trying to figure out like what to do. If you haven't played with ChatGPT, you should really work with it. The other day I was like, hey, what's the difference between finite strip method? Yeah, I was like, what's the difference between finite strip method and finite element method? Because one of the students was asking. I was like, I don't know, but Chat knows. So I went with Chat. We're on a first day basis. When you start using it, maybe I mentioned this before, just always be polite. Please and thank yous. Because when they take over the world, right, they can always say that Mike Berry was polite to them, right? I always said please and thank you, even when it was wrong. We got in a big argument last year. Because I was talking to her about geosynchronous orbit velocities, and I was trying to get escape velocities from it, actually, and it kept giving me orbital velocities, and I was like, no, I want escape velocities. Not escape velocity would be what your minimum velocity would be required to get shot off the Earth and not come back, right? And then it was giving me, and we were just back and forth, a little banter, right? And I could not convince it, but. And then I got into this. Just show you some stuff. Like I had a friend that he was trying to sell hay, okay? He was one of the professors over here, Tim White. He was trying to sell hay, and it was just super boring. So I said, hey, I was like, can you try? I'm trying to sell here. Here's the specifics. Help me make this sound great so it sells with a couple sentences. And so like, high quality hay rounds, 1,200. I was like, that's okay. Can you make it fancier, please? Right? And they says, here's more. Premium quality hay rounds weighing 1,250 pounds, right? And then I said, come on. Can you make it like a used car commercial? Hay alert. You won't believe your eyes. Top tier hay rounds, price to move. Firework emoji. We're talking big, 1,250-pound rounds, wrapped in both net and twine for extra durability. It's funny. That's funny. Let me give you this one. Oh yeah, I put Trump. I put a Trump's language too. It'll do that. Yeah, sell it like Trump, and it did. Okay, so how about haiku about this one always gets me. Haiku about students learning about orbital mechanics at Montana State. These would get me. Its haikus just blow my mind. Let's see what the haiku says here. Orbits twist and turn. Montana skies hold the key. Knowledge flies like stars. Huh? Let's see. The other. We just. If you haven't done it, my God, it blows my mind every day. But you gotta be careful because it's not always right. Circling the void's edge, students' dreams of stars in flight. Montana guides them. Okay. Work in Bobcats. Because we're Bobcats, right? You should know that too. Orbital paths in the sites. Montana's pride source. Yeah, that's right. Can you give me an image? I'm sorry. Sorry. Because I put the oven, threw her off. Let's see. Let's see what she comes up with here. Sometimes it impresses me. I don't know if it is. Oh, there it is. Huh? I know, right? It's not bad. That's not bad. Can you make them bobcats? Let's see. Let's see. Let's see what she comes up with here. If you that's what I'm saying. If you haven't worked with this yet, you should really work with it. There we go. Right? It's trippy. One more. Okay, let's see what she comes up with here. Sometimes I get upset that it takes so long, and then I realize, like, look what it just did. Like, look what it's doing. Oh, but come on. Now this is getting a little ridiculous. But if it's listening to me, you're okay. Just do what you need to do. All right, we'll come back to that one. All right, we're not done yet. By this is kind of all we're covering today. So, but I got some more stuff. Okay, one thing that irritates me, absolutely irritates me to no end, is when I watch a movie. This is what engineering did to me. It ruined lots of things for me because what really throws me off is if I'm watching a movie and the mechanics are wrong. Right? There's something wrong. Like the physics are wrong. It's like, you gotta be kidding me. Like, sell this to me. Like, let me be in the moment. I can't be in the moment because I'm just like I mean, everybody's seen the movie Speed, right? The speed and the bus jumps. It makes no sense. The trajectory of that bus is not parabolic, right? It blows my mind. But the worst one I've ever seen was the movie Gravity. Have you ever seen the movie Gravity? The movie Gravity, there's a scene in there that is like, there's supposed to be the most intense scene of the whole thing. And it's just, they ruined it, right? Because the whole time I'm just like, who's behind this? And we'll watch it. We'll watch it in a second. So I'll give you the situation. Right? There's some sort of space junk out in space, right? We got the satellite, and we've got this things like this, and there's like this, and then they got these people. There's a tether coming out, and then there's Sandra Bullock, right? She's kind of attached to the tether, right? She's like this, and then she's got a little rope that's going from her out to George Clooney, right? I got George Clooney out here, going like that, okay? And so they're flying along the way, right? They're flying along, and then they were propelled from like an explosion or something like that, and they're going along. And Sandra Bullock gets hung up first, and then she gets hung up in the cable. And then George Clooney comes by, and she grabs George Clooney, right? And George Clooney has this initial velocity as it's going away, right? And then as soon as George Clooney gets a certain distance away, goes away, and then boom. And if you look at the free body diagram, what happens, right? This guy goes out, just think of it as just like one system. And then we'll look at George, we'll look at here, like Sandra Bullock, right? And there's this, sure, when George Clooney goes by, right? And there's, he has initial velocity like this. It's traveling to the right like that, okay? It's traveling to the right, and it has some initial velocity. But as soon as he stops that initial velocity, there will need to be some acceleration, right? As he's floating away, if he's floating away to the right and we want to stop him, he's got to accelerate that way because he has a velocity to the right, he's got to accelerate back to the left. And absolutely, when that happened, right, there would be, in order to get the acceleration back to the left, there would be tension in that cable. Absolutely, right? I mean, like everybody would agree that would happen, right? Because he's traveling to the right, he's got an initial velocity, and then he's got to accelerate back to the left if he's going to stop, and then so there would be a tension in that force. But what happens as soon as he stops moving? There's nothing there anymore, right? The two of them would just be floating right next to each other. There's no other forces there, right? There doesn't need to be a tension. He doesn't need to accelerate this direction anymore. Right? If Sandra pulled on it, absolutely, there'd be a tension in that cable. And then George would start accelerating back towards him. Right? I mean, right? But if they're just sitting there, they just float next to each other. Nobody's moving. Nobody's accelerating. No tension in any forces. Right? Or no tension in any of the objects. Okay, so let's watch. Let's watch this. All right. All right. Let's see, gravity. There we go. No. Gravity clip. All right, Matt Kowalski. Oh, also, spoiler alert. But it's okay because this movie's really old. But if you haven't seen it, there's a spoiler, okay? So just spoiler alert, I think is what you're supposed to say. I mean, obviously the title of it, Matt Kowalski's death, kind of gives it away a little bit. Watch an ad first. Right there. He stopped. Right? He stopped, right? You saw that, right? And so clearly, right, there should be no tension in that force anymore, or no tension in that cable anymore, right? Because he stopped. If there was tension in the cable, that would be a force. It would cause him to start accelerating back the other way. But he's not accelerating. He's just holding steady. What would be the one way that he could have tension in that?
Aren't they spinning? Because she was going
Yeah.
around initially.
Yeah.
So.
Yeah, so that's exactly right. You could happen if the thing was spinning, right? Because if it was going around, it would be like a ball on the end of a string whipping around, and they would for the centripetal accelerations, there would have to be a tension in it. But
just hold on. I'm gonna start pulling you in.
Hey, Doc.
Just hold on. Hang
Hold on.
on. I'm gonna pull you in.
Ryan, listen.
I want to see. They show it right there. They're not spinning, right? Yeah.
They are. In that scene, they are.
Where?
Press play. It's pause.
They don't show spinning. I don't see the spin. I don't see spin. I don't see spin. Oh, motherfucker, I hit the wrong button. Okay. I don't see spin. I don't see spin.
Right. Trace out their like exposition, right? So they're here,
Yeah.
right? So
Where'd you
now-
come from?
So now play the video for just like put it on slow speed.
I don't know how to do that.
Go to the top right settings.
Yeah.
The gear at the top right.
It won't let me hit it.
Playback speed.
Playback speed. Playback half. 0.5.
I don't know. That's not enough. That's not enough.
The thing's moving behind you relative to her position.
Yeah, or she moving relative to it. But my point, if they didn't make it clear enough, even if it was spinning, right? Like in the movie, in Interstellar, right? There's a scene where they're spinning, and they make it really evident that shit's spinning. But in this case, there's no evidence that that thing's spinning. Just maybe slow it down to half speed and then put my finger on the board. Then I can see that it's spinning. But at the time, I watched this in the theaters, and at the time, I'm like, it's an imaginary force pulling on him. This is bullshit. Yeah.
You gotta, like, earlier, she is spinning faster.
Wait. I got some evidence against you. Okay. All right. Wait. You're right. I got you, right? Because I absolutely, I got you. I got you son of a bitch. I got you right where I want. I got it. Watch it. I get you.
Just hold on. And I'm gonna start pulling you in.
Hey, Doc.
Just hold on, hang on. I'm gonna pull you in.
Ryan, listen.
Pull you in.
You have to let me go.
No.
The ropes are too loose.
Don't be
I'm pulling you with me. You have to let me go, or we both
Let
die.
you go, we're fine.
You son of a bitch. You son of a bitch. There's no spinning at all. There's no spinning at all. What's spinning? I don't see it. It's moving. It's not spinning.
Ryan, let go. It's not up to
How
you.
about this? Wait.
You're gonna make it, Ryan.
If that son of a bitch was spinning, then for her perspective, I'm assuming this is from her perspective, perspective would have been going like this, and he would have been drifting off to the right. But that's not what, he's just drifting away. They have imaginary force. Also, if there was an imaginary force pulling on it, what would he be doing? He'd be accelerating away, and he's not accelerating away, he's just drifting away at a constant velocity. There's no acceleration. They blew it. I disagree. I'm gonna do some calcs to see how fast the thing would have to be spinning in order for it to yank on him as hard as it was. Because even if he was spinning, he wasn't spinning fast enough.
We know the size of the ISS, and we
Yeah.
can see their relative position through the ISS.
We can. I agree. They blew it. See? Now he's spinning. That's right. See? She's not spinning. She's not spinning. You see it there. Those angles there. So the whole time it's supposed to be everybody's in the audience is crying, and I'm just like, this is bullshit. Their physics are wrong.
She's also accelerating back.
What's that?
She's accelerating back to that.
That also wouldn't make sense either. Right? Why would she accelerate back when she let go of them? She wouldn't. She wouldn't. That one wouldn't happen. They blew it, right? They had a chance to capture young minds and show them how physics work, and they blow it. Later on, when we look at conservation of momentum, we're gonna return to space. We're gonna return to space and watch another video that they nail it. Yeah. I'd say the crowd is in an uproar right now. They're upset.
Picture.
Oh, let's go back to the picture, yeah. Well, let's look at a couple. While we're on YouTube, let's. All right. So he dies. He goes on to die. So this is interesting. This is an interesting concept.
I'm Jack Black. Oh, that's it. Yeah. I'm not Jack.
So this is a clip from Interstellar. This is related to what we were just talking about. And this is a concept that shows up in several sci-fi things. This physics right here is pretty good, right? This has to do with the centripetal acceleration component of it. So if something's in orbit, so if something's rotating around, so they have a big old disc like this. Big old disc like this traveling around in a circle, and you have a person. This is how they do artificial gravity in a lot of things, right? And this thing's got an omega like this. If it's rotating around with an omega, there would have to be a force that's pushing on there, right? And because this person in here would want to accelerate out, but then the surface is preventing it from doing that. And so there would be a force like this, and this is how they do artificial gravity in like sci-fi stuff. So they do this in Interstellar. They also did this in Ender's Game. If you ever read Ender's Game or watched the movie Ender's Game, that's the premise behind that. Is they live out here where there's gravity, and then they come into the middle to battle, right, in 0G and stuff. Because in the middle, your radius is 0, so you got 0 gravity in the middle of this thing. So this is an Interstellar clip. There's no if you haven't seen Interstellar, it's pretty good. I thought the physics were pretty good, like the whole relative, the theory of relativity and stuff. All that's good until the whole black hole thing. Traveling back in times, But I didn't buy that. Everything else. Have you seen it? Again, if the movie is over 10 years old, I'm okay. Just give it away spoilers. Right? If you should see it. Does he look? He's on a space station. Like, oh, what's happening here? Right, so they built basically this big spaceship that's just a big circle that's always rotating, and it's rotating at a velocity such that when you're out near the surface there, you feel gravity, right? And that's it. And so then you kind of artificial gravity. I thought that was kind of an interesting scene. You should watch this movie. It's a good movie. Except for the black hole thing.
The station isn't named after you, sir.
Right. You guys have you seen Starlink satellites yet? Yeah. Did you see that?
I saw it launch.
You did, yeah.
1 a.m. and I'm driving through the bridge of Canyon and it's zero, just things shooting up to the ground. I thought they launched them.
Yeah. You're like, yeah. It's Starlink. It's setting up those satellites for the thing. They go up in. This is at the launch, right? This is at the launch. They go up like this, and then they disperse. But I've seen it a couple of times. And then it kind of freaks me out a little bit to think about how many satellites are out there and how many there are gonna be, right? Because there's this theory that we can Earth lock ourselves, that you get too much space junk up there and these things start hitting each other and then we can never launch off of the Earth because there's all these things. Yeah, I know. And then, well, it turns out space is really big. I think that's what it is. That's what it is. It is huge, massive. But if you get enough up there, then they can run into that. Okay. I think that's the one. I thought you used to have some. What are you seeing?
You got right into the window.
The what? Oh, someone right there did? Oh man, I missed it. How did they leave?
I want to know how.
Yeah, are they spitting? Anyways, all right, that's all I have for you. We'll pick up on the next subject next time.